and welcome to this video series on creating an instruction set simulator in C. The purpose of this video series is to create software to simulate the DLX architecture by reading in a DLX assembly file and interpreting and executing the commands in that file. If you're uncertain about what DLX is, you can definitely check out the Wikipedia page, which explains it in great detail and definitely goes over a lot of the technical sides of the DLX. But to quickly summarize, it was designed by John Hennessy and David Patterson, who had previously designed MIPS. DLX was designed to be more modern and simpler than MIPS and is now widely used for educational purposes as a result. DLX is 32-bit and it's a RISC architecture with only 64 instructions, but it does have the ability to actually have some extended instructions added in. The Wikipedia page covers all this and more, and we'll definitely touch a lot more on the DLX architecture as we need to for designing the software. So the project has a pretty simple roadmap. We're going to start off with a small primer on function pointers and jump tables. If you already know those two things, you can definitely skip the rest of this video and continue on. If you're unfamiliar with those or you want a little bit of a refresher on them, you can watch the rest of this video and get an idea. And if at that point you're still not sure, there's definitely tons of resources available online that'll explain them to you. After that, we're going to start with stage 1 of this project, where we'll develop a single cycle data path machine. In that stage, what we're going to do is we're going to create a cycle-based state machine that will start by fetching an instruction and then decoding that instruction, executing the instruction, and then accessing the memory if it needs to, as well as writing back to the registers if it needs to. One DLX instruction will go through all 5 stages before the next instruction executes, which is why it's single cycle. And from there we'll implement as many of the instructions as we can, excluding things like jumping and branching, because we won't have, it'll be an interpreted instruction set at that point. We won't have actual file with a program counter. Stage 2 will implement file I/O, so reading an entire file in, which is where we'll implement the program counter and the remaining jump and branch instructions. And then after that, we'll work on making this a more optimized simulator by using a pipeline state machine where a new instruction is executed every cycle, and data hazards are handled using no operations as well as instruction reordering. So with that, that kind of covers a little bit of an intro on the project. So we'll start with our little primer, and then from there we'll start working on the project. Alright, so we'll start with our primer here. I've just got a small little main.c, which is a C file that we'll use to kind of demonstrate functions, pointers, and jump tables. So to start out with, if you're unfamiliar with function pointers, it's basically a way of storing a function in a variable. You may think, this is crazy, why would I ever want to store a function in a variable when I can just call the variable? Well, there's some niche areas where it is definitely beneficial. And at this time, it might kind of be hard to see that, but it's very beneficial when writing something like an instruction set simulator. So the way you create a function pointer is you start by using a type def. And with a type def, what you'll do is you'll first start by writing a function definition the same way you would, or function declaration, sorry, the same way you would if you were to put it into a header file. So we start with our return type, which we'll say is void in this case, and then we have this little weird bracket, asterisk, bracket, and in here we're going to put the name of our type def. So the same way you would go type def, I should spell it right, type def unsigned int uint. What's written here is uint is the name of the type def, or what unsigned int is type def as. So what we want to type def our function pointer as is what we'll put here. So in this case, let's do something simple and just say greet. And then we put in our parameter, which we'll say is void or no parameter. So this is our function pointer, and if we want to create a variable to hold a function that this can point to, we go to and do a greeting. So this here is our function pointer variable. So the same way, this is a int pointer, this is a function pointer. It's just got a little bit different syntax because we type def it differently. So now let's create a function that actually conforms to this type def. So we have void as the return value. We'll call it hello as the name, and it takes in no parameters. And what we'll have it do is we'll have it just printf and hello world. So now, if this were just a regular program, no function pointers being used, we would just call hello, and it'll print out hello world. Now, we don't want to do that. We want to use function pointers. For whatever reason in this project, that's what we want to do. So we'll start off by going greeting, and then we'll say greeting equals hello. So this is kind of weird because normally when you call hello, you have the brackets after, since it is a function call. But because we're storing it in a variable, we don't need them. Now, the same way you would call hello by putting the parentheses after, we're going to call it by just doing the same thing but with greeting instead. So what this is going to do is it's going to say, hey, let's go to greeting, and let's use the value stored there as the address of the function we want to execute. So the same way a pointer has the address of the variable or the value or the location in memory where the value is stored, this has the location in memory where the function is stored. So I'm going to quickly just put in, since Visual Studio does close the command prompt right away, I'm just going to put in a scanf to kind of make it delay until we're ready to close it. I'm using the Visual Studio 2015 on Windows 7 with all the default settings, so I have to use scanf_s since it's a security risk, they say, to use scanf. All you have to do is just set some compiler flags and it won't say that anymore. I just haven't gone to and done that. So if you're using anything else, you won't have to put the _s there. But now if we run this, it will print out hello world because it's calling the function located at the address that greeting reference stores. So it works the same way a pointer does. It's just instead of accessing a value, it accesses code that executes. Now, that's a function pointer, really simple. Now the reason it's super nice is because we can create something called a jump table or a branch table, which is, on a very simple level, an array of function pointers. So now we have an array of function pointers, or a jump branch table. So what we can do is we can have a second function here, void good day, where we printf and we print out good day. And now we can store these as, we can put these into our jump table. So we have greeting, and we have hello, and then we have good day. So now we can call these functions by getting the address in array value or array location 0 and calling it. And then we can do the same thing by calling the second one. So this will do the same thing that it did before. It's just now, instead of saying we want the value of greeting, or we want the address stored in greeting, we're saying we want the address stored in greeting index 0 or greeting index 1. So now if we run this, it'll print hello world and then good day. So the reason this is really useful is because we can create a table of functions that are our instructions. So we could have one for add, one for subtract, one for multiply, one for load, one for store. And each of them will do whatever they need to do, and we can access them by calling an array value. So when our instruction has an operation code of, let's say, well, let's just do it right here. So we have our instructions, and it's got an int opcode equals uh, 0. Okay, so that's the opcode we've decoded from our instruction. Well, now we'll go to our jump table and we'll say, well, call greeting opcode. And now if we run this, it still prints hello world. So that's why jump tables are super useful. They're really easy once you understand function pointers, and function pointers are really easy when you understand pointers. So at the end of the day, it's all really simple. But it's also going to be the most advanced we're going to get with this project, which is why it's easy to cover now. So with that, we're now ready to start by creating our simple state machine, which we'll start in the next video.